So we talked about gravitational potential energy. The other form of potential energy, mechanical potential energy, that we want to talk about is we want to talk about spring potential. In order to come up with a useful equation for spring potential, I need to go back to the beginning. Okay, the true equation for work. Okay, we said it was F dot D, force times displacement, but it's a dot product in between the two. We have to go back to the real equation for that. It turns out that when we're talking about work, the true equation is the summation of force dot dr. Okay, and then you're going from R1 to R2. I'm trying to remember if I did that right. It may be the other way around. But you're going between 2 points. Okay? Now, why does that make a difference? Well, the force that we're talking about is spring potential. Okay? The equation for that is going to be negative kx, and this is not going to be dr anymore. It's going to be dx. Okay? My displacement is not referring to some radius value. That's what r is standing for. It's just some radius. You go from one point to another point that's defined as a radius and a displacement, obviously. But now we're just talking about in the direction of the spring, x, okay, in that kx equation. So when I do the integration of that, I end up with my spring potential energy have an equation of 1/2 kx squared. Okay? So that means that the energy that's stored inside that spring is going to be equal to 1/2 kx squared. Now, in all honesty, it should be delta kx squared. Okay? It's the change from equilibrium. If you remember, springs have a natural equilibrium, have a natural length. And it's the change. If I compress the spring that way, it's the change in x that stores its energy. So if I go in this compression, I'm creating energy. I'm going in this direction. I'm creating energy. I'm storing energy. I'm not really creating it. Okay, so that's what we mean by spring potential energy. That's what we mean by delta x. It's the change from its equilibrium point that creates energy. You can say that the object is at equilibrium, and that gives me an x value, but it doesn't mean that it has energy. It's only when that spring is compressed or expanded that we get that energy. Okay? And it's a real simple equation. It's really not terribly useful to talk about it for 6 minutes, but 1/2 k delta x squared. It's referring to the k constant, which is the property of the spring, and then this delta x is either the compression or the expansion of that spring from the equilibrium point. Okay? Spring potential energy.